Hello friends, good afternoon everyone. I am fine. How are you? I hope you will be fine. Welcome back in my channel Dr. Satendra Kumar. Dear friends, if you want this type of videos relative to mathematics for higher level, then you need to subscribe, share and like my videos and my channel. Today we will discuss continuity and limits of two variable functions. Okay. Now first, simultaneous and iterated limit. Simultaneous and iterated limits or repeated limits. We can define several kinds of limits. We can define several kind of limits for a function fxy of two variables x and y. Okay, let a comma b is a limit point of a set is a limit point of a set of values in two-dimensional space then we have the following limits. Now discuss again simultaneous and iterated limits or repeated limit. We can define several kind of limits for a function fxy of two variables in x and y variables. Let a be is a limit point of a set of values in two-dimensional space. Then we have the following limits. Number first, limit x comma y tending to a comma b fxy. It can also be written as limit x tending to a y tending to b fxy. This is called simultaneous limit. Okay, we repeat again. Limit x y tending to a b fxy. It can also be written as limit x tending to a y tending to b fxy. This is called simultaneous limit. Now second kind, limit x tending to a limit y tending to b fxy comma limit y tending to b limit x tending to a fxy. This is called the iterated. This is called iterated limits or repeated limits. These two limits may or may not equal. Okay. First limit extending to a, after this limit y tending to b in fxy. Similarly, first limit y tending to b and secondary limit extending to a in fxy. This is called iterated limits or repeated limits. These two limits may or may not be equal. Now, note here's first note. The simultaneous limit of function fxy exists and is equal to L at x comma y tending to a comma b. If for every epsilon greater than 0, comma there exists a delta greater than 0 such that fxy minus L modulus lesser than epsilon. For all values of x and y, for all values of x for all, this is sign of for all values of x and y in the neighborhood of open interval AB defined by x minus a modulus lesser delta, comma y minus b modulus lesser delta. Okay, this is the definition of simultaneous limit. If the repeated limits are not equal, now second note, if the repeated limits are not equal, the simultaneous limit cannot exist. Okay. Now second note is very important. Now repeat again. If the repeated limit are not equal, the simultaneous limit cannot exist. Okay. Now there are some problem. Now problem number first. Prove that the simultaneous limit Prove that the simultaneous limit x comma y tending to 0 comma 0 y sin 1 upon x exists and equal to 0, but the single limit x tending to 0 y sin 1 upon x, where y is not equal to 0, does not exist. Okay. Now solution is, let epsilon greater than 0 and take delta is equal to epsilon such that x का modulus lesser delta, or we can say greater than 0. Similarly, y का modulus greater than 0 lesser than delta. Then we have y sin 1 upon x minus 0 modulus lesser equal y modulus into modulus of sin 1 upon x. Okay, since the modulus of sin 1 upon x always lesser or equal to 1, now this value will be lesser equal y, but y is lesser than delta and delta is equal to epsilon. Okay, imply that y sin 1 upon x minus 0 modulus lesser epsilon. Therefore, limit x comma y tending to 0 comma 0 y sin 1 upon x is equal to 0. This is the simultaneous limit. Limit is exist and equal to 0. Okay, but for simple limit or single limit, when y is not equal to 0, for single limit x tending to 0 y sin 1 upon x, this is equal to y, since value of sin lie between -1 to +1. Okay, this is not unique. Okay, that is limit x tending to 0 y sin 1 upon x does not exist. Okay, student. Second problem number 2. Prove that simultaneous limit x comma y tending to 0 comma 0 x y cube upon x square plus y to the power 6 does not exist. Okay, now answer is Let us suppose that xy point approaches along the line y is equal to x. Okay. Now that is at y is equal to x. Imply that x tending to 0. Then we get limit xy tending to 0, 0 xy cube upon x square plus y to the power 6. This can be written as x to the power 4 x square plus x to the power 6 limit x tending to 0. Now x square upon 1 plus x to the power 4 limit x tending to 0, that is we get 0. But again xy approaches xy approaches 0, 0 along the curve x is equal to y cube. Okay, that is x tending to 0. Now we can write limit x, y tending to 0, 0 xy cube upon x square plus y 6. Now limit x tending to 0 along y cube is equal to x, that is x square. Now x square plus x square, this is equal to x square upon 2x square. Now limit x tending to 0. Now x square cancel by this x square, this is equal to 1. This is independent of value of x. Therefore, these two iterated limits are exist but not equal. Therefore, simultaneous limit does not exist. Okay? Or we can say along two paths. We can write since along two paths we get different limiting values. So the simultaneous limit does not exist. Okay. Now third problem, prove that limit xy tending to 0, 0 xy x square minus y square upon x square plus y square equal to 0. Now solution. Let epsilon greater than 0 be given for every x, y not equal to 0, 0. Now we have xy into x square minus y square upon x square plus y square minus 0 whole modulus. This is equal to xy into x square minus y square upon x square plus y square. This is equal to lesser x square minus y square xy modulus upon x square plus y square, xy modulus. Okay, this is represented by equation number first. Now we know that x modulus minus y modulus whole square always positive. Therefore, x modulus square plus y modulus square minus 2, x modulus y modulus always greater than 0. Or we can say x square plus y square always greater than 2xy modulus. Okay, now imply that xy modulus upon x square plus y square lesser 1 upon 2. If xy is not equal to 0, 0. Now putting the value of xy modulus x square plus y square here. Now from equation number first, xy into x square minus y square upon x square plus y square minus 0 modulus always lesser x square minus y square modulus upon 2. This is always lesser than x square plus y square upon 2. This equivalent epsilon if x square lesser than epsilon and y square lesser than epsilon, lesser or equal, that is x का modulus lesser under root epsilon and y का modulus lesser or equal under root epsilon. We take or we choose epsilon equal to under root or delta is equal to under root epsilon. We can write xy into x square minus y square upon x square plus y square minus 0 always lesser epsilon. Whenever x modulus lesser than delta or we can say greater than 0, comma y modulus lesser than delta or greater than 0. This is the definition of limits. That is, we can write limit xy tending to 0, 0 of function. Now function is xy x square minus y square upon x square plus y square always equivalent to 0. Okay.